Mathematics is often taught as a series of abstract symbols on a page, but the logic of the subject lives in the physical world. We use it every time we organize a workspace, manage a budget, or solve a structural puzzle. Consider this toy shop inventory. The teddy bears, dolls, and cars are scattered without obvious order, a raw data set. To analyze this data, we physically sort the objects. By separating the dolls and the elephants, we create distinct categories that can be counted and compared. Once the groups are sorted, the numbers become clear. This chart shows 4 teddy bears compared to 3 elephants. The bears are the larger group, while the elephants are fewer in number. Organizing information by specific attributes like type or color is the first step in solving any mathematical problem. It turns a chaotic pile of objects into a structured set of facts. Now, imagine you are the shopkeeper responsible for managing the store's resources. You are working with a budget, which acts as a hard limit on your spending. This forces you to make strategic choices about how to distribute your available units. We use abstract numbers to represent these physical quantities. For example, a single card marked with the number 5 carries the same weight as 5 individual tokens combined. If you need to reach a target value of 7, you can use different combinations of resources. You might count out 7 single units, or you could combine a 5-unit card and a 2-unit token to reach the same result. This flexibility allows you to solve equations using whatever resources you have available, even if you don't have the exact units specified in the problem. Try this yourself. This toy car costs 8 units, and you have a pool of 1s, 2s, and 3s. Pause the video and find a way to reach the total of 8 without using 8 individual 1s. You could have grouped 4 2s together or used 2 3s and a 2. Both combinations satisfy the requirements of the price tag. Combining these values prepares you for puzzles where part of the information is missing. Think of a missing number equation as a physical scale. To keep the scale level, the total weight added to the left side must be identical to the weight on the right. The equal sign marks the center of this scale, indicating that both sides of the problem exist in a state of verified balance. We can apply these principles to more complex problems, like a grid puzzle. Here, we must place 4 different types of objects, buttons, pebbles, seeds, and clay balls, into a 4x4 square. The challenge is satisfying 2 rules. No object repeats horizontally or vertically. Focusing only on rows hides mistakes. Here, the row is correct, but a duplicate piece violates the column rule. Shifting this duplicate slot resolves the conflict, satisfying all constraints. Managing these overlapping constraints forces you to look at the entire system rather than focusing on a single row. To recap, first, always organize and categorize your information before you start your analysis. Second, use different combinations of values to adapt to the resources you have available. Finally, verify your answers against every rule of the problem to ensure your solution is balanced. Mathematical patterns become clear when you move concepts off the page and work through the logic with physical objects.